In 7.2, we're going to look at, for the first time in calculus, calculating a volume. We've used integrals to calculate areas, the different figures, but now we're going to look at calculating volumes. And in the past, in geometry, things we've been able to calculate volumes of, or for example, volume of a cube or a prism, we could get the volume by doing length times width times height. Or if we had a cylinder, we could take the cross-sectional area times the height or the length of it. And lots of different things. If we had a sphere, let's see, what is that? 4/3 pi r cubed gives you the volume of a sphere. So in geometry, there are lots of different volumes we can calculate, lots of different shapes we can calculate the volume of. But as we get into calculus, if we have a surface defined by a function and we want to use it to generate a volume, then chances are there's not a specialized geometric formula to let us calculate that volume. So let's look at some examples of some things that we could generate from a curve. So here in Inventor, I've drawn a parabola, and I have from A to B, I have a section, and we have an enclosed area here. So we have this enclosed area. Now if we take that area and revolve it around various points, that's going to create a volume. So let's take that, and the first time, let's rotate that around the x-axis. So notice if I take that figure and I rotate it around the x-axis, we get some type of bell. And that's three-dimensional, so that's got a volume. So that's something that might be useful. We might need to know that internal volume. We could take that same shape and rotate it around the y-axis instead of the x-axis. We get a completely different volume. Same cross-sectional area that we began with, but we rotated it around somewhere else. Let's pick a vertical line that's not the y-axis, rotate it around. Yeah, something kind of looks like a wheel, maybe. Or an inverted donut. Of course, there's a volume to that. We rotate that around a horizontal line that's not the x-axis, so we can get that figure. So depending on our cross-section, depending on where we revolve it, there are lots of different shapes we can generate. So one thing that you'll need to always keep in mind is just trying to visualize what is your shape going to look like. Now, a project that we do in lab has us calculate the volume of a dam, and that dam comes from doing a revolution of a specific cross-section. If we take this cross-section here and rotate it around a certain axis, if we rotate it all the way around, it would look something like that. But we're going to rotate it about 150 degrees, and that's going to give us an image of a dam holding back water. And in our project, what we're going to do is we're going to try to calculate how much concrete it would take to pour that dam. So let's look at, well, how would we calculate some of these volumes? So let's begin. Let's take just a generic function. Let's say we're going to take it from A to B, and we want to rotate that around the x-axis. So let's take a sample element that's vertical. And if we think about rotating that sample element around the x-axis, that's going to generate a disk. Think about if we were to take that and rotate it. We would have something like a penny, a coin, a disk. That disk is going to have, if we look at it from looking down the x-axis, it's going to have a cross section that's a circle. From this side, looking at it, it's going to have a thickness. So in order to calculate the volume of that, that's just a cylinder. The way you calculate the volume of a cylinder is you take the cross-sectional area, that's a circle, so the area is pi squared, and then you multiply it times the height of that cylinder. Well, in this case, if this is our function, then that's our radius, because keep in mind this is going to rotate and it's going to come down here as well. So from here down to there, that would be our diameter, so that's our radius. The height of our cylinder is our thickness, dx. So our volume will be pi r squared dx for each one of those little cylinders, and we're going to add those up from A to B. So we're going to take each little sample element, rotate it around the x-axis, get a little disk, and we're going to add up all of those disks. So if we're wanting to add up, then that's a summation, an integration from A to B, pi r squared dx, where in our case here, r squared is given by our function. Now let's take a look at an example of rotating something instead of around the x-axis, around the y-axis. So let's suppose we could even take a straight line. And let's see, let's take from here to here. And let's take that and rotate it around the y-axis. So imagine if we rotate that around, we basically get a cone. So we need to figure out, well, how can we calculate the volume of that? So as with rotating around the x-axis, notice our sample element is perpendicular to the axis of rotation. Our axis of rotation was horizontal, our sample element was vertical. So here, if our axis of rotation is vertical, our sample element will be horizontal, which means it's going to have a thickness dy. Let's suppose this function is, our input is y, so let's call that f of y. So if we rotate that around, we're going to have lots of little disks. So we imagine our disk, let's suppose this is the y-axis, then our radius will be that distance. So a cross section of that is going to be a circle, so that will be pi r squared. The thickness of that is dy. So we're going to add all of those up from bottom to top. So integrate pi r squared dy. So in this case, that distance will be r. So r, in this case, will be just given by whatever f of y is. And remember, that will be an x value. You put a y in, you get an x out. So pi r squared from A to B, where A and B are y values. So let's do an example. Let's suppose we do that same type of problem. Let's suppose that our line that we're rotating around the y-axis is given by the equation y equals 2x plus 1. So here this point is 0, 1. When x is 0, y is 1. And let's go up to here. Let's see, if I just pick a random x, when x is 3, y is 7. So this is at a height of 7. So if we want to use the disk method, which is the name of this method, we'll draw our sample element to be perpendicular to the axis of rotation. It's going to have a thickness dy, and this distance is just whatever the x value is there. So we need this as a function of y. So we need to solve it for x. So at this point, solve that for x, y minus 1 over 2 is that x value. If we were to move it down here, if you tell me what the y value is here, I'll put it in and tell you the x. Here, y is 1. If we put a 1 in for y, 1 minus 1 is 0 over 2, so x is 0. Here, if you put a 7 in for y, 7 minus 1 is 6 over 2 is 3. So notice as this goes up, the x value of that is changing. It's getting wider and wider. So we want our input to be y, and that x value is going to tell us how tall that is. So we're going to integrate from this y value up to this y value. Pi r squared, pi is a constant, so it can stay out front. R, this distance, is given by our x value, which is y minus 1 over 2. You could think of this as f of y. So the x value here is given by y minus 1 over 2, or you could call that f of y. So that's our radius. So pi, our radius squared times the thickness, dy. So in this case, it's pi, the integral from 1 to 7 of y minus 1 over 2 all squared dy. Now when we square that, we get a 4 on bottom, which is just a multiplicative constant, so just bring that out front. When we square the numerator, we get y squared minus 2y plus 1. That's just a polynomial, so we can integrate that. Y cubed over 3, 2y squared over 2, so y squared plus y. We want to evaluate that from 1 to 7. So put a 7 in, do pi over 4 times 7 cubed let's see, 7 cubed, 343 over 3 minus 7 squared plus 7 minus all of that with a 1 put in. So 1 cubed, so 1 over 3 minus 1 squared plus 1. So those cancel. So notice both sides have a pi over 4, so we can pull a pi over 4 out. Then you have 343 thirds minus 49 plus 7, that's minus 42, minus a 1/3. Notice we've already factored that common factor out front. So pi over 4 times common denominator, subtract the numerators. 3 goes into that. 3 goes into 3 one time. 3 goes into 4 once with 1 left over. 3 goes into 12 4 times. So pi over 4 times, let's see, what's 114 minus 42, 72, which is divisible by 4. 4 goes into 72 18 times. So that volume would be 18 pi. So rotating that around the y-axis, so having a sample element of dy. So if we rotate and our sample element is dy, then our volume is pi times the integral from a to b of r y squared dy. If we integrate with a dx sample element, then we integrate pi r of x squared dx. So we have a function of x when it's dx, a function of y when it's dy. Now, going back to here, and even this one, when we did some of our revolutions, depending on what we rotated around, notice sometimes we have a hole. So if we have a hole, we have to be a little bit careful, because the radius to the outside, we're going to account for some volume in the middle that that's not part of our actual figure. So let's look at an example. If we take, let's see, let's suppose we have a line here and then a horizontal line here. And let's suppose we were to take that and rotate it around the x-axis. So if we were to rotate that around the x-axis, then this is going to rotate around. Notice there's a hole in here. So when this is flipped over, your hole is going to go over to here, come on down. So this is going to be on around like this. So it's kind of like a cone with a hole through the middle of it. So if we didn't have that hole, if we went all the way to the axis of rotation with our sample element, then that would give us the volume as if we were to take all of that and rotate it around. So I'm going to call that distance from the outside to the axis of rotation, I'm going to call that big R. Notice our sample element is dx. So if we were to take all the volume from here going all the way to the center, then when we rotate that sample element, pi r squared times the thickness gives us the volume of one of those disks, and then we integrate that, of course, from A to B. But that accounts for some volume that we don't need. We don't want to take into consideration, or we don't want to have that volume of that hole inside. So just imagine drilling a hole straight through there. So if we can get that volume and take it away, that'll give us the volume of the outside part. So, oops, I'll take that away. So if we imagine that volume goes from the axis of rotation to here, and I'm going to refer to that radius as little r. So that volume, rotate that sample element, which is a dx element, that's a disk. So the cross-sectional area would be pi little r squared times the thickness. We're going to add those up from the left side to the right side. Now if we subtract those, that'll give us our resulting volume of the outside part, then taking the hole out. So if we put that together, that's pi, the integral from AB r squared. Actually, let's do this. If we move the pi inside, notice since the integrals both go from A to B, then this integral from A to B is pi big R squared. This integral that we're taking away is pi from A to B of little r squared. Pi is a common factor, so bring out the constant pi. We're going to take r, which will be a function of x squared, minus little r, which will be a function of x squared dx. Which, don't confuse that, that's not big R of x minus little r of x all squared. You can't subtract the radii first and then square it. It's the outside radius squared minus the inside radius squared because of that. So if we have a hole in the middle, and we have a dx element, big R squared minus little r squared dx. If we have a dy element, pi from A to B, capital R of y squared minus little r of y squared dy. So this is with a vertical sample element. This was with the horizontal. And remember that for this disk method, that the axis of rotation is perpendicular to your sample element. This is technically called the washer method, because if you take, if the axis of rotation is not touching the inside edge and you rotate that around, then you're going to get a washer. Like such. But the way you calculate the volume of that is you take the volume from the, if you were to do the whole thing, minus the volume of the inside, and that'll give you the volume of the washer. So the washer method, which is just an extension of the shell method, not the shell method, the disk method. So let's do an example of that. Also, we're going to use an axis of rotation that is not on the X or the Y axis. So let's see, let's take y equals x squared and let's see, let's take y equals 2, and let's rotate that around, make that a dotted line. Let's rotate that around y equals -3. So instead of rotating this around the x-axis, we're going to rotate it around this line, which is below the x-axis. So our cross-sectional area, not our cross-sectional area, but our enclosed area that's being rotated around is this, and this is getting rotated around this line. So our cross-sectional area, our D element, since our rotation is horizontal, then we need a vertical element. So big R will be the distance from the outside of our rotation to here. And since this is dx, that'll be a function of x. Little r will be from our axis of rotation to the inside of our washer. So little r of x. Now notice this is a constant, y equals 2. So let's figure out big R. This distance, whether we're here, whether we're here, whether we're here, if we take the outer minus the axis of rotation, 2 minus -3, we get 5. That distance is always going to be 5 because that's a straight line, a horizontal line. Now, little r is going to change. The farther we get over, the larger this distance becomes. Here, little r is larger than little r is here. So little r, if we take the top, which that y value is given by our function x squared, and subtract this y value is -3, then little r be given by x squared plus 3. Now let's test that out just to make sure that little r works. So here, if we think about our function, when x is 0, y is 0. Well, here our little r is 3. The distance from here to here is 3. Well, if we put 0 in to little r, we get 0 plus 3, which is 3. For here, and I said y is 2 there. I shouldn't have necessarily done that. When y is 2, then x, I guess, is the square root of 2. So that point is the square root of 2. So if we put the square root of 2 in, we get Square root of 2 squared is 2 plus 3, which is 5. And notice that distance is 5. This is 3, that's 2, so little r here is 5. So now that we have big R and little r, then our volume is pi times the integral from left to right. So here x is 0. Here x is the square root of 2. Big R squared minus little r squared dx. So pi times the integral from 0 to root 2 of 25. Let's see, if we square that, get x to the 4th, 6x squared plus 9. So if we distribute a negative, that'll be minus x to the 4th minus 6x squared minus 9. So pi times the integral from 0 to root 2, 25 minus 9 minus x to the 4th minus 6 x squared dx. So for time's sake, you can integrate that on your own, just a basic antiderivative, and evaluate that from 0 to root 2. So the biggest trick on this was finding r. So let's go back again and remind ourselves, well, how did we get big R and little r? So big R is the distance from the outside edge to the axis of rotation. Well, on this one, the outside edge is always at 2 minus the inside edge, which is at negative 3. And then for little r is the distance from the bottom of our sample element to the axis of rotation. So this distance is y minus this y value is negative 3. Notice this y is changing, and this y is given by the function y equals x squared. So that height minus this height gives you little r. So that little height, we could call that f of x. So you could think of it as a f of x minus this y. So f of x is x squared, so x squared plus 3. Then you just substitute into your formula. So that's the shell method, disk method. I keep on calling it shell method. That's the disk method. Or in this case, since it's got a hole, also known as the washer method.